Okay, today we're going to be talking about section 2.8 from your textbook. So if you want to look in your textbook and follow along, that's fine. I will also be putting a PDF of this document that I'll be working with in the video on Brightspace, so you can follow along there as well. Today we'll be talking about subspaces of Rn. So let's get started. A subspace of Rn is a set that has the 0 vector in it. Any two vectors that are in your subspace, if you add them together, that's also in your subspace. And you can take any scalar multiple of a vector in your subspace, which will also be in your subspace. A good way to visualize this is a plane. So for instance, if we have this plane in three-dimensional space, and you can imagine this plane goes on forever, this is a subspace of three-dimensional space. You can see that the plane goes through the origin, so 0 is in it. If I take any two vectors in it and I add them together, because this plane sort of goes on forever, those will still be in it as well. And any scalar multiple will be in it too. More to the point of what we've been talking about, spans are subspace. So if you think of the set of linear combinations of any vector, that is going to be a subspace. 0 is in the span. Any vector in the span is a linear combination of our base set of vectors. So if we add two vectors together, they'll still be a linear combination. And similarly, if we take any scalar multiple, we can just scale that linear combination. So spans are also subspaces. There are two main subspaces that we're going to focus on today. One is column space and one is null space. So let's start by talking about the column space. The column space of a matrix is the set of all the linear combinations that we can make out of those columns. So this is just the span of the columns in A. So this is the set of all the B such that AX equals B has a solution. So if we're thinking about AX equals B, if this thing is consistent, so this is consistent. If this thing is consistent, then that means we have a solution. We have an X that this works for. So in that case, B is a linear combination, which means it's in the span, which is another way of saying the column space of A. Sorry, B is in that column space of A. Yeah. So if our system is consistent, then B is in the column space. That's all that means. Right? Okay, so let's take a look at what this looks like in practice. So this is problem 6 from your textbook in section 2.8. So our question is, here's our matrix A. Is this vector in the column space? Well, what do we do anytime we have a problem? We turn it into an augmented matrix and try to reduce that thing. So here in the blue, I've put this as an augmented matrix where we're saying, if I let my B be the augmented part, is there a solution? Is there an X? So we go ahead and reduce this by row reduction magic, and we get down here. So does this work? Is this system consistent? Well, it's not, because in fact we have two problems, 0 equals 23 and also 0 equals 17. So this is not consistent. Consistent. This is not consistent. So what does that mean? This means that B is not in the column space of A, where this thing is B. Yeah? Okay, so hopefully you're feeling a little bit better about column spaces now. Let's move on to our second thing, our second subspace that we're going to talk about, which is the null space. So the null space of a matrix is the set of all solutions to that homogeneous system AX equals 0. So whereas our column spaces we're looking at B, our null spaces are looking at X. So what is the set of X for which this works? So we're looking at the set of X that satisfies that solution. Okay, so this is, we've done a lot of stuff with this before, like parametric vector form. That was looking at our solution sets. That solution set is called the null space. We'll see an example of that in a second. Before we move on, I want to say one more thing. We can ask ourselves what a basis is for a subspace. So a basis for a subspace is a linearly independent set that spans that subspace. So we can think of a basis as sort of the building blocks that we can use to build up our subspace, our maybe little one by one Lego bricks that we can use to build our subspace. And we've actually seen bases before. So for example, a standard basis that we've looked at before is we've looked at those elementary column vectors. So, So we looked at those elementary column vectors, E1, E2, however many of them you need. Let's say we're looking at E3. These are a basis for R3. So remember what these standard column vectors are. They're just the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these are linearly independent by definition. And they span because any vector that we might want to have in R3, let's pick an arbitrary one, x1, x2, x3, we can write this as a linear combination of these standard basis vectors. So this is, I can take x1 copies of E1 plus x2 copies of E2 plus x3 copies of E3. Yeah. So this is showing us that this spans all of R3, and you can see that they're linearly independent because if we put those into a matrix, we only have a unique solution for a homogeneous system there. Okay, so let's combine the null space and the basis to answer their problem out of the textbook. So this is problem 24 from section 2.8. So we're going to look at this matrix A, and our question is, what is the null space of this? And then what is the basis for that null space? Well, if we start off asking what is the null space, how do we find this? Well, what do we do? Anytime we have a question, we go ahead and make an augmented matrix. So this time we're going to augment with the 0 vector because the null space is dealing with homogeneous systems. And then we're going to go ahead and reduce that down to reduced row echelon form. And then if we want to know what the null space is, this is just the set of all solutions, but we already know how to do that. That's parametric vector form. So what we might want to do for this is we say, all right, we want to know what the vector x is going to look like. So this is the vector x1, x2, x3, and x4. We want to know what possibilities we have for that. Well, if we look, we can see that x1 plus 3x2, x1 minus 3x2 plus 3 halves x4 equals 0. That's coming from our first row of our matrix. So I can solve for x1 and say that x1 equals 3 copies of x2 minus 3 halves copies of x4. x2, well, that's just itself. x2 is a free variable. x3 equals minus 5/4 copies of x4. And x4 is also just itself because x4 is again a free variable. So we have 2 free variables here, which means if we want to write this in parametric vector form, then we can factor out our x2. And how many copies of x2 does x1 have? It has 3 copies. x2 has 1 copy. There are no x2s in x3, and there are no x2s in x4. And then to that, we can add on factoring out x4. So that's going to give us, there are minus 3 halves copies of x4 and x1, no copies in x2, minus 5/4 copies in x4, and 1 copy in x4. Sorry, minus 5/4 copies in x3. Okay, so this right here, this space, let's maybe highlight that. This is our null space right in here. So this is the null space of A. This is the set of all solutions. So any solution can be written like that. Now, our second question is, what is the basis for this? Well, we see that any vector, so our basis needs 2 things. It needs to span and it needs to be linearly independent. And we can see that every vector in the null space can be written as a linear combination of these 2 vectors. Let's call this U and let's call this V. So by the definition of our null space in parametric vector form, we can see that anything in our null space can be written as a linear combination of u and v. So our question is, are they linearly independent? So we already know they span. Our second piece is, are they linearly independent? So in other words, is there any way to get 0, 0, or the 0 vector at the end without the weights both being 0? And the answer for that is no, because if x is going to equal the 0 vector, then all 4 variables would need to be 0, and that would include x2 and x4. But those are the weights of our 2 vectors. So that means that u and v are also linearly independent. So the basis for our null set, or for our null space, is going to be this set of vectors u and v. Okay. What if we wanted to find a basis for the column space? So we just saw how to find the basis for the null space. What if we wanted to find a basis for the column space? So let's imagine that we're looking at our same A, and we want the basis for the column space of A instead. Well, we'd want a set that spans and a set that's linearly independent. By definition of the column space, those columns span the column space, right? That's what it means to be in the column space, because the column space is just looking at the span of the columns. So they already span, so our second piece is linearly independent. So we want to check, are those columns linearly independent? If they are, then it's a linearly independent set that spans, so it's a basis and we're done. If they aren't linearly independent, then some of those columns can be written as linear combinations of the others. So if we take those things that can be written as linear combinations of the others out, then the remaining columns will still span, since the ones we took out were effectively redundant, but now the remaining columns will also be linearly independent, and we have our basis. So if we're trying to find a basis, basically we want to look at which columns do we want to keep that'll stay linearly independent. Well, how do we decide? The columns that can be written as linear combinations of the other ones, we can think of as associated with free variables. So we should keep the ones that are not associated with free variables. In other words, the ones that have pivots. And this leads us to our theorem. So if you didn't follow any of that, tune back into the theorem. So the theorem is that the pivot columns of a matrix form our basis for the column space of A. So if we want to know the basis for the column space of A, we want to find which columns are pivot columns. So let's actually answer that question that we posed on the last page. So this is back to problem 24. So for that same A, we want to find the basis for the column space of A. So we go ahead and we take A, and what do we do with it? The only thing we know how to, so we can reduce that down to reducer echelon form. And, well, the basis is formed from the columns that have pivot position. So which columns are those? Well, they're the first and the third, right? So the first and the third column, those are the ones with pivot positions. So those are the ones that have the basis. So our basis for the column space is going to be the first column of A, which in this case is -3 to -3, and the third column of A, which is -2, 4, -2. So this is our basis. Okay, so to recap, what have we talked about today? We've talked about what is a subspace, and then we talked about the two subspaces that we are particularly going to care about, namely the column space, which is the span of the columns of A, and the null space, which is the solution set to the homogeneous system. And we also talked about what is a basis, so what are the vectors that can build up our subspaces that we're interested in, and we saw how to find the basis for the null space and the column space. If you have any questions about this, please feel free to either email me or sign up for my virtual office hours. And I'll be posting another video soon.